This is the governing equation for single phase flow. After discretization with the finite difference method, you can write the equation in matrix form. T is transmissibility matrix. X is your vector of primary variables. For single phase flow, it's going to be pressure of grid block 1, pressure in grid block 2, pressure in grid block 3, up to the last grid block. For two-phase oil and water flow, it's going to be pressure in grid block 1, saturation, water saturation in grid block 1, pressure in grid block 2, water saturation in grid block 2, and so on. B is your accumulation matrix, and I can upload a video where I actually derived all of these in PEDI 4056 if you guys are interested, but remember, our focus will be on finite volume methods, so there's no need to go into all of the details here. This is the derivative of your solution vector. This is your source or sink term. If we assume 1D steady state model with all the coefficients set to 1, so transmissibility is basically 1, then what we have is Laplacian of pressure equals Q. Just a simplistic form to show you how you differentiate this term. And if you already watched the video on Taylor series, you will realize you can approximate this continuous derivative using the central difference approximation to the second order derivative, which gets you this. And the right hand side is just Q for every grid block I. And so you can use this expression and then substitute when I equals 1, and you obtain this. When I equals 2, you obtain this. When I equals 3, you obtain these. And it's important to realize these are simultaneous equations, and as such can be written in matrix form, which is given on the next slide. Again, these are the equations from the previous slide, and we want to show how to write it in matrix form. This is what you get. How? So this is equation 1, and it should be on row 1. It's basically row 1, which is all of this. This is important, right? Row 1 multiplied by the solution vector. When you multiply row 1 by the solution vector, what you get is equation 1. So 1 over 8 squared, right? I've taken this out. And you're left with the numerator. So how do you get P2 minus 2P1 plus P0 as the coefficient? This is P1, right? What's the coefficient of P1? Is minus 2. So you put minus 2 here. So that multiplies P1 and you get minus 2. What's the coefficient for P2? Right here. It's 1, right? So you put 1 here. This is going to multiply P3. Do you have P3 in equation 1? No. So you put in 0. No P4, 0, right? No P5, 0 for all the other terms. P0 does not exist, but is treated as a boundary condition, and so we'll bring it into the right-hand side. And what that means is you have P0 over H squared, right, taken to the right-hand side, so you have Q1 minus P0 over H squared. And that's what you put on the right-hand side here. So multiplying row 1 by the solution vector will be equal to this guy to get equation 1. Equation 2 is also similar. We've taken out the 1 over 8 squared, so we just need to focus on the numerator. What's the coefficient of P1? 1. Right? It's going to be multiplying the solution vector. So to get equation 2, you're here. So the second row multiplied by the solution vector being equal to the second row of this vector gets you equation 2. And so coefficient of P1 is 1. This guy is going to be coefficient of what? P2 minus 2. And this will be coefficient of P3, 1. Other terms are zeros. And equation 3 and so on continues until you get to 6, if you're looking at 6 grid blocks. And the right hand, we're assuming you have the boundaries here, and just like we did here, right, on this boundary you get this. This is just showing you how you move from linear systems of equations. So if you have equations 1, equations 2, equations 3, and so on, you can convert them into a matrix form to solve it simultaneously using matrix solution methods. And this system of equations you're looking at is basically A, right? This is A, matrix A. And this is your solution variable X, right? Equals, we can write it as small x. So it's basically AX equals B. AX, and this is B, your right hand side, equals B. And we have several numerical methods for solving these systems of equation. In MATLAB, easiest way to solve it is A\B, and you're done. The system of equation is linear. Why? Because we assumed the transmissibility matrix was basically 1, or an identity matrix. I shouldn't say that. We assume the permeability is basically 1, because we're solving Laplacian of P equals Q. But in the real case of reservoir simulation, you'll be solving K over mu B, right? Grad P. And this mu can be, mu and B are functions of pressure and saturations respectively. And so you're not just going to have this transmissibility matrix. But the focus on this slide is on how to move from systems of equations to matrices, which I believe is clear. And that's what you're going to continue to do even for finite volume and finite element methods. So we have different ways to solve AX equals B. You can use direct solvers like LU factorization with forward and backward substitution. These are standard linear algebra procedures. It's limited to block structured meshes. And the important thing about direct solvers is they will converge in a fixed number of iterations. Whereas iterative solvers can converge in different number of iterations depending on the iterative solver you are using. Direct solvers use a lot of memory when your system of equation is large, and it quickly gets out of hand when your system is very large. So for very large systems, say 1 million grid blocks, for instance, you don't want to use direct solvers. The memory required will be too much and it will not work. So that's where iterative solvers shine, because they use less memory. But if you have very small systems, you can use direct solvers. Examples of iterative solvers are Krylov subspace solvers like GMRS, generalized minimum residual method, BICG by conjugate gradient method, BICG stab by conjugate gradient stabilized methods. And I said you can simply use backslash operator in MATLAB and you get the results. And then what MATLAB does is to figure out the best solver depending on the structure of your matrix, A or T in this case.